So, I'm going to talk to you today about my dissertation project. I've done an investigation into GPGPU-enabled file carving, and if you don't know what that is, I will explain it, hopefully. So, I'm Corey Forbes. I've recently left Aletheia, the university that doesn't exist, the northwest side of the world. I've just also finished work at the Scottish Business Resilience Centre, and I'm moving down here to work at MWR, so that's going to be fun. So what is file carving? I hope everyone here knows. Does anyone want to put their hand up if they do actually know what file carving is? Okay, maybe not then. File carving is the collection of files on the raw hard disk. Because when files are deleted, they're not really removed, they're just dereferenced. So what we do is we drop down to the physical level and we search the contents of a hard disk or backing storage. So the quote here excellently summarizes that the metadata that holds all of the file locations is fragile. That gets completely wiped and when a file is deleted. But when it is deleted, it's still actually in the physical disk layout. So you can see here that the track sectors are when the disk sectors and the tracks meet, and that typically holds your individual chunks of a file. But the operating system usually deals with this for you. The files are broken down into these chunks and appropriately placed about the disk. And this can be in the two ways you can see here, which is fragmented files, where the file's too big to be stored all together and is thrown throughout the disk. It's a pain in the arse. And contiguous file allocation is when the file's all kept together and it's just linearly placed. This is quite good when you're working with physical hard disks that have the actuator arms that move about, because you just read all in one go. When it comes to disks as well, with these actuator arms, that helps me segue into the fact that backing storage has only recently became fast enough that it's now the software's fault that it's not, or that everything's starting to get slow from a file carving perspective. So SSDs and RAID technology has helped shift the attention of these programs back into the limelight in terms of needing improvement. So ultimately, my research question was how fast can the header-footer search become, or how fast can I get the header-footer search to find these files? And to clarify, the headers and footers are unique, identification at the start and the end that say this is a PDF or this is a JPEG. So Aletheia helped me get a solid answer to the question, but to better explain, just to make sure, or to figure out where the problem was, I had to break down what file carving programs do. So it just comes down to the two halves of searching for these files and these header-footer pairs, as well as the actual carving. But the carving, it can only get so quick before you start to lose accuracy. And so the header-footer pairs is entirely the searching for these pairs is entirely where my efforts were focused. So I'll quickly talk about searching algorithms. I don't want to ruin everyone's day here. So Boyer-Moore is what the current tools Foremost and Scalpel make use of. These are the two open source CPU file carving tools that I was comparing against. Boyer-Moore uses two rule sets to jump through a string that it's searching, and it helps save time, but it requires the CPU to be fast enough. I'm not going to go through everything on the slide, but it's more for the video for anyone who wants to look back at it. Boyer-Moore also has to pre-compile these jumps, so it's not very fit for purpose with this new hardware I was trying to bring into the process. So as such, I moved to a new algorithm, which is the parallel failureless Aho-Korosic. It's a dumbed-down version of the Aho-Korosic algorithm, which will allow, or which basically will act as a brute force search, but for multiple patterns simultaneously. Forgot to mention, actually, Boyer-Moore can only search for one string at a time, so having the ability to search for multiple is where a big step up also comes in, which we'll see in the results later. But having this more towards brute force search helps with the fact that each compute core on a GPU is a bit stupid in comparison to the CPU, where it's all fast and smart. So now that the background's out of the way, we can discuss the development. So I made use of C++ as well as the CUDA library to develop the Aletheia toolset. But CUDA then limited me to only being able to use NVIDIA hardware. So as such, I wanted to bring back the usability. At the time, I didn't actually realize AMD are looking into adopting CUDA, so that would have worked well to know. And okay. So yeah, cross-platform development was then a big objective of mine. I wanted to get it working on both Windows and Linux. So then the other goal, of course, was I wanted open source file carvers to be hopefully or I wanted to be in the leads and compared to those. Foremost and Scalpel being CPU based, I was hoping that I could proof of concept that GPU is the way forward. So for my results, I used both my personal desktop, which was running Windows, and an AWS instance on Linux. I've just got this for clarity's purposes. Again, it can be looked at later. AWS was really useful for being able to recreate my results for anyone who wanted to look at it themselves. So you can see here that Scalpel is both the fastest and the slowest between the two tools. Specifically, it's worth noting that the Boyer-Moore algorithm I discussed, how it searches for only one string at a time, was made perfectly clear by the fact that it had to do multiple passes. Thus, when I was searching for all the patterns instead of just PDF patterns, the data throughput dropped drastically. You then compare this to Aletheia, which was a vast improvement, and when you compare PDF only to all patterns, you can see there's a lot less drop-off, or a lot less of an extreme drop-off on the data throughputs. So I was hoping as well, that's just ticking away. So for future work, I was really hoping that I could even apply this to a real-time memory forensics use case. A hypervisor, for example, could be running a tool very similar, or a repurposed version of the final project in the event I do implement the full file carving features. And it could search for malicious files that exist in live memory. So, but yeah, that's all I have in terms of my slides, but I'm open to any questions or heckles.
Heckles?
Yeah.
First, any questions? No? I'll ask one then. So while you were doing this, did you look at the device free list, not the dev free list, but the inode free list in the Unix systems to see if that might be a good starting place, or did you just look at the file system raw?
So I was just looking at how fast I could get this specific process to go. Just looking at file carving itself, I haven't looked.
So you just scraped the entire drive? You didn't look at a free list off the drive?
Yeah. Specifically with my AWS instance as well, I wanted to test my algorithm more, so I even made use of RAM disks to load the contents that I wanted searched, and it was just all about the speed of the algorithm. So. And
did you look through the bad block table as well, or did you?
No, I was going for a stupid approach, as it were. Yeah.
Okay. Other questions? Now that the tough ones are out of the way. That was actually how I got started in security, doing that.
Oh, fantastic.
41 years ago.
Yeah.
Hello.
Hi, Sam.
Hi, Corey. I was just wondering, what do you think about the feasibility of tools like Foremost implementing a GPU-based approach? Do you think that might happen, or do you think it would have to be
Scalpel tried it, but their code isn't good. I heckled them on GitHub, and they responded with their attempt. And I mean, yeah, they could absolutely adopt it. It's just a matter of proof of concept and hopefully being able to circulate this knowledge throughout the sphere, and it would be applied, hopefully, in the future. So.
When you say it's not good, did you mean it wasn't parallelizable, or was it not vectorizable?
So they did manage to parallelize their results, but they also, it was as if they're really good computer scientists, but they just obviously aren't good at parallel performance. They just didn't understand how to do it correctly, and ultimately it just didn't work out well for them.
Other questions? Comments? Ideas? Okay, thank you.